Hey team, it's Mr. Zimmerman, and today we're going to do folds, turns, and zeros, and basically it's just getting started on this next section of our unit. Let's go ahead and warm up. All right, take a moment, pause, write down the warm-ups in your notebook, and take a moment to read through some of the words for the learning goals. We'll come back at the end. So, number one, we essentially have to distribute, and I know many of you like to use the algebraic way where you kind of just imagine, hey, I multiply x and I'm going to multiply it by x squared and -5. I'm going to go ahead and take a moment to show off the area model. So if I was using an area model to represent it, I'm going to be multiplying x by two things. So I'm multiplying x, and I have to multiply it by x squared and -5. So this is what you're doing when you draw that arrow. So x times x squared is going to result in a third x to the third. X times -5 is going to be -5x. Hence, that's the answer. Notice how it went from two different terms. I write it in standard form, going from descending order. This next one, again, most of you would multiply like so. And then you would distribute the -1 to both of those terms. This is going to be the same process. Now, I am going to use a 2 by 2 square because I have multiple terms. I have x minus 1. I have x plus 4. Notice how this is the opposite of factoring. I'm starting on the outside. X times x is x squared. X times -1 is -1x. And x times 4 is going to be a positive 4x. Finally, -1 times 4 is -4. So I'm going to write it in order. X squared. -1x and 4x is going to result in a positive 3x minus 4. All right, in number 3, basically I have to multiply 3 terms together. I'm going to choose to multiply these two together first. It's going to be a similar process to number 2. Then I'm going to multiply whatever the answer is by x. So let me go ahead and start out my area model. It's going to be x plus 1, and then it's going to be 1/2 x plus 1. So let's go ahead and figure out each entry. 1/2 times x, you have to remember that there's an invisible 1 in front of all variables. There's one variable there. So 1 times 1/2 is going to be a half, and x times x is going to be x squared. Again, 1/2 times positive 1 is going to result in 1/2. Multiply the numbers, add the letter. 1 times 1 is going to be 1. Deal with the letters. 1 times 1 is going to be 1. Again, these are all positive. So when I write out my answer, it's going to be x times 1/2 x squared. 1 and 1/2 make 1 and 1/2 x plus 1. Now the final thing I would need to do here is to distribute my x. So I'm going to go ahead and just add an x term to each of my terms. So this is going to be equal to 1/2, add an x to the third, plus 1 and 1/2 x squared. 1 times x, 1x. Now, if you want, you can choose to represent 1 and 1/2 as positive 3/2. That is okay as well. All right, number 4. Kind of like number 3, I can go in any order. In the above problem, I chose to multiply these two together first. To show you that multiplication, order doesn't matter, I'm going to go ahead and multiply these two together before I multiply by x plus 2. So let me create my area model. 2x plus 1, x plus 2. There's going to be 4 entries. 2x times x is going to be 2x squared. X times 1 is 1x. 2 times 2x is 4x. And 2 times 1 is 2. I'm going to take a moment to write this out. Going in order. 2x squared, 4x and 1x make 5x's plus 2. How do I remember it's positive? Well, when there's no sign, you assume it's positive. So now, what I basically did was I took this expression, 2x squared plus 5x plus 2, and now I need to multiply it by x plus 2. If I wanted to show off my area model here, I can do it again. Okay, so let's set it up. Notice, I have how many terms? 1, 2, 3. 2x squared, 5x, positive 2. What am I multiplying it by? Well, x and positive 2. Watch what it creates instead. So, 2 terms, 2 terms times 3 terms is going to result in 6 terms. Let's start multiplying. 2x squared times x is going to be 2x cubed. 5x times x is going to be 5x squared. 2 times x is going to be 2x. Let's go ahead and multiply positive 2 now. 2 times 2x squared is going to be 4x squared. 2 times 5x is going to be 10x. And 2 times 2 is going to be 4. Now, all of these terms are going to be my answer. Before I take the information out of the area model, I am going to take the opportunity to combine like terms. So, this is going to result in my leading term, 2x to the third. It's degree 3 because this is going to be the highest degree. Now I'm going to look. 5x squared and 4x squared is 9x squared. 2 and 10x is 12x. And then 4. So even though I had 6 terms as a result of this multiplication, it turned out to be simplified. Notice this is a degree 3 because the highest exponent is 3. Okay. All of these, we were using the distributive property to rewrite each expression. I do want to take a note, a lesson from the past, is that the answers are an equivalent expression to the distributive form. So, you have transformed functions by constant values to create new functions of the same degree. How can you use transformations to create higher degree functions? This is going to be the question to answer at the end. Go back, test your understanding when you are done, and answer this to the best of your ability. So, let's get to the getting started. So consider the constant function f of x equals 3. Remember, f of x is a fancy way to say the output. This is the answer typically, and it is always represented by y. You can imagine this as y is 3. The graph of this function is a horizontal line crossing the y-axis at 0, 3. Okay, on site, this is a what kind of intercept? Y-intercept. The reason I know immediately is look at this graph. Put a point here, put a different one below, to the left of the origin, and above. Notice 0, 3. This point would be on to the left or right 0, and it would be a positive number. Here, this would be some positive number, 0. Below, it would be 0 to the left and right, and it would be some negative value for y. And then over here, it would be some negative value, 0, because it's not up or down from the origin. So, by this equation being equal to 3, what it is saying is y is equal to 3. All coordinates will have a output of 3. So for example, when x is 1, well, y is 3. X is 1, y is 3. Notice how it's here. X is 2. Okay, doesn't matter. Y is 3. Becomes 2, 3. So on. X is 3. Doesn't matter. Y is 3. 3, 3. Notice how this process repeated is going to result in a horizontal line. So, essentially what you need to take away from this is assumed knowledge from the past, that when it is y equal to some number, you have to remember it is a horizontal line. Why? Think about what happened. All of the y values are fixed. There is no math to be done. The input doesn't actually affect the output. Okay. Recall that you can translate this function vertically by adding a constant. Every point on the line is translated vertically by the constant. But think about a transformation in which the d value is not a constant. So, suppose a function f of x is equal to 3 is translated by x to the form 3 plus x. This would mean that the y value of every point on the line, y equals 3, is translated by its corresponding x value. Let's go ahead and kind of break down what's happening and go step by step. So we're going to consider the original function at x equals 1. Okay, x equals 1. So I'm going to go ahead, use this purple color. When x is equal to 1, notice where it's at. It's at 1, 3. After a vertical translation of x, to vertically translate something, you are going to go ahead and take your equation, and I'm translating it by x. Well, what did I say x was? Well, x is 1. When x is 1, the output is 4. So after this translation, this point is going to go ahead and go to 1, 4. So this point is going to move there. Number 2, consider the point of the original function at x equals -1. Okay, it's at -1, 3. Because remember, the input doesn't actually change it, it's just 3. But now we're going to try to vertically translate it by x. So our original guy that we're going to try to translate x unit In this case, I plug in and evaluate 3 minus 1. That's going to result in 2, meaning after this transformation, when x is negative 1, the y value will be 2. Notice how it kind of changed differently. And that's to be expected. We're not just changing it positively. We're not changing all of them negatively. We're changing it by x. We're changing it. Sometimes we're going to translate it up. When you add a number, it goes up on the graph. When you subtract a number, it goes vertically down the graph. So number 3 is saying plot other points after applying a vertical translation of x. What function is formed by translating all the points? Now we're not going to do all, but we're going to do a couple more just to see what happens. If I were to take f of 2, that would mean 3 plus 2. That would mean when x is 2, the output is 5, meaning 2 comma 5 would be the new point. So I'm going to erase the old points because this is going to get scattered. It's going to go from, well, what's my input? 2, 3, but it's going to turn into 2 comma 5. I hope you can see how, since I am adjusting my vertical translation to positive 2, notice how this point changed. Positive 2. If I were to change the same thing, and I would say negative 1, 3 minus 1 would result in an output of 2. That would give me a point negative 1, 2. Going back to my graph, my input was negative 2. Now it's going to be negative 2 comma negative 1. Okay, I hope you can see right now. Like, look, if I connect these dots. Oops, this point is supposed to be here. Okay, so the idea is you can identify a pattern. Since we're going to be adding x, notice how the transformation makes it a diagonal line. Oh, let's keep going. So this point, we're going to have to figure out for the next question, what number or what coordinate was not translated. What point does not change its location from the original function to the new function? And why? So, what point didn't change? Well, looking at the graph, right here, the y-intercept is still the y-intercept. Let's go ahead and look at that. The y-intercept, and what this means by definition, is what is equal to 0. It goes 0 to the left, and it's some number. This is true always. If I plugged in f of 0 into my function, 3 plus 0, do you see how it's unaffected? Why doesn't it change its place? Because our vertical translations are adjusted by the input. Here, x is 0. So 0 vertical movement. It does not move. The next question asks us, what's a 0? Well, 0 is a x-intercept. So 3 plus x, notice our function, f of x, is 3 plus x. If I want to think of it in slope-intercept form, when y is equal to mx plus b, I could come to a bunch of conclusions and say x, or m, the slope is 1, x plus 3, if I rewrite it in that order, it is a degree 1 because there's an invisible 1 to the exponent, which means it's going to have 1, 0, or 1 x-intercept. The x-intercept here is negative 3 comma 0. Now remember, how was this created? That's the question. All of our points came from this original line, right over here, this line. Everything started from there. Well, think about how it's created. This is all a translation. In order for it to be created, how far does this point have to go to reach the x-axis? 1, 2, 3. So I could predict that where would it be equal to the x-intercept? Here, this point, because the line is 3 units above the x-axis, meaning to create the x-intercept, the root, I'm going to have to move it down 3. I could predict that. So, essentially what we got to say, how is the 0 created? Well, the 0 is created by the introduction of x. The 0 is always a x-intercept. Before the graph would have never touched it. Until we vertically translated by adding x. Pause it. Rewrite that. Notice what happened. By introducing this x, we took a line that was completely horizontal, and we're going to be vertically changing it by a rate. It will be 1, it will be 2, it will be -1, it will be -2, and it ends up making it look like a positive slope. And this adjustment, we vertically translated it, created this x-intercept. It was not there in the first place. Hope this helped, team. This has been good.